All right, so last time we talked about recognizable and decidable languages. Here's where they are on the map of the Chomsky hierarchy. The decidable languages are right outside all of the other ones that we've seen so far. Here's the regular languages, things like A star, context-free languages like A to the N, B to the N, and palindromes. P and NP we will talk about. It's complicated. And then there's a bunch of other decidable languages out here that take longer and longer times and more space to recognize. You can prove all sorts of hierarchy theorems here. There's an infinite number of languages in each of these categories. And finally, all of these are decidable. So the decidable is this big outer oval here in this Venn diagram, this set containment diagram. All these sets are proper, except possibly P and NP. We don't know if that's proper or not. That's literally worth $1 million. Bounty from the Clay Institute. Everything else we know to be proper. All right. So the recognizable languages are outside the decidable, of course, including all the decidable, but there's more recognizable stuff that's not decidable, like the halting problem. And so here's the halting problem. It's recognizable, so it's right here. This is a whole language. It's an infinite language, this little dot here, which is really a circle full of strings. The complement of the halting problem is not even recognizable, so that's outside this oval. So that's the map so far, right? We've seen this picture before, but now you're more familiar with the different regions of this picture, and as we go further, you'll be familiar with yet more regions here. Any questions about that? So these are not sets of strings, they're sets of languages. It's sets of strings. Keep the type in mind here very clearly, otherwise you'll get confused. We started covering reductions. We said this is this innocent-looking picture that's really very subtle and deep and applies to a lot of scenarios that you wouldn't even imagine. We gave examples of a couple of simple theorems. We said if A reduces to B, and B is decidable, and A is decidable. And by the way, the reduction preserves members to members and non-members to non-members. That's important right here. Otherwise, it'll just be a function. It wouldn't be a special function called a reduction. It doesn't have to be one-to-one. Lots of things can collide in the range. But if A reduces to B and A is undecidable, B must be undecidable either. That's just a contrapositive of the first, but you can prove it from first principles like we did the first one. And we gave an example. We said, this is towards the end of last lecture, we said the halting problem on the empty string. If you just run a program on no input at all, just let it run, see what happens. Does it halt or doesn't it halt? And we gave a reduction according to this little diagram we just saw. And the reduction was, we know that the halting problem in general is undecidable. So take an arbitrary instance of the halting problem, right? The halting problem comes in the door, it has a machine and a string, or a program and an input, it's equivalent. And you want to know what this machine will do on this string, what this program will do on this input. So what do? Given an arbitrary machine and an input, construct a brand new machine from these two. Once they walked in the door, we can take them and manipulate them and create a new machine from them, we being the reducer, the thing that maps the reduction. Just another algorithm, program, compiler, if you will. I'm going to create a program that does the following. It takes M and W into its finite control, its hardwired strings, constants in the program. Because once I walk in the door, we can create a program where some variable is the W and some other variable is the M. Okay? And then that program ignores its own input and instead simulates M and W. Those are both hardwired into it. It knows what a program is, and it knows what the input is, and you can just simulate M and W internally. Easy to do. Just simulate, right? Any compiler can do this. But of course, this program is not being run. It's being constructed. It's been written down as code. Be very clear about that. We're not running this program that does this. We're constructing it over here. Okay. And it accepts its own input, whatever it may be, its own X, if and only if internally M halts on W. So that's what this program does. How many get this? Pretty straightforward, right? Except if we had an oracle for the halting problem on the empty string, we can take this program that we just constructed, and this program now is called M prime, and we gave it a name in purple. We can take this m prime and feed it to the oracle, to this subroutine that supposedly tells us what a program or an algorithm or a Turing machine does on the empty string. Maybe it's easier than the holding problem. Who knows? In a second, we'll see it's not. But the words contradiction assume that there's some program, algorithm, oracle, code, or machine that does this job, tells us what a machine does or a program does on the empty string. Special case of the halting problem. Right? And if it tells us that this m prime halts on the empty string, we know that m halts on w. If it tells us that it doesn't halt on the empty string, we know that m doesn't halt on w. Why? Because this program, m prime, halts on all of its input x if and only if m halts on w internally. In fact, it ignores its input, does exactly the same thing no matter what its input is. It's oblivious to its own input. Instead, it just simulates m on w internally, no matter what the input is. So if m halts on w, it'll accept each and every one of its inputs. If m doesn't halt on w, it will not accept each and every one of its inputs. How many get that? It does the same thing every single time. It's pretty boring, this program. Except it simulates m on w. So if we had a subroutine that can tell us what an arbitrary program does on the empty string, we can feed this to that subroutine, and that oracle will say, yeah, it halts, which means m halted on w, or must halt on w, for it to accept the empty string, or any string, because its behavior is identical on every single string in the universe in sigma star. And so an oracle like that, just being able to solve the halting problem on an empty string, we exploited it into solving the halting problem on any string. End of theorem. So that must be undecidable also. How many get this proof? All right, it's only 5 people. Ask me questions then. Let's go over it again. I mean, if you don't understand this, there's no way you'll understand what's coming up next in 20 minutes, which is Rice's theorem, which is an abstract generalization of this. So if you think this is abstract already, you ain't seen nothing yet. All right. What are we trying to do? We're trying to prove that the halting problem on the empty string is just as hard, as difficult, as intractable, as impossible as the halting problem on any arbitrary string. Why would we even ask this question? Let's say you don't know how to do arbitrary multiplication in your head. So I say, okay, what's 2 times 3? And you say 6. I say, wait a second, you said you couldn't do arbitrary multiplication in your head. But then you say, well, but 2 times 3 is easy, because it's just too small number. It's a special case of multiplication. That one I got. All right? The halting problem. We know that there's no algorithm for the halting problem. But that doesn't mean that specific special cases of the halting problem can't be solved. It means that in general it can't be solved, like arbitrary multiplication in your head. So if I say, here's a program, begin, end. That's it, 2 statements. Begin, end the program. I say, does it halt? And you say, yeah, of course it halts. And I say, how did you know the halting problem is unsolvable? How did you pull it off? Well, because it's a special case. It's like a 2 times 3. It's easy. There's many, many special cases. While, true, begin, end, that runs forever. How did you know the halting problem is unsolvable? Well, because it's a special, simple, easy, special case. How many understand that? So whenever you have a hard problem, you try to special case it, create specific, easier instances, fix some variables to constants, and see if it remains hard or if it becomes easier. Right? It's a natural thing to do. Try to figure out when the problem becomes hard. When you start piling on all these constraints and requirements and variables and generalizations, eventually becomes very hard. But when did this threshold happen? When did this phase transition happen from going to easy to hard? I can do this multiplication. I can say 2 times 3. You say 6. Okay. 7 times 8. That may take you a few seconds. But if I say 1, 2, 3, 4 times 7, 8, 9, 10, digits, that could take you many minutes. Maybe you won't even get it if you try to do it in your head. So there's a certain phase transition when the problem becomes from trivial to hard, and at some point impossible, like the halting problem. So that's what we're going after, to figure out where this transition is, where this phase transition is with respect to problems like the halting problem. So if I say, I'm not going to ask you arbitrary instances of the halting problem, I'm going to ask you only instances of the halting problem when given the empty string. Not an arbitrary string, the empty string. So that problem no longer has 2 parameters, m and w. It has 1 parameter, m, because the other one is fixed at empty, no input. And the question now is on the table, is that question easier or harder than the halting problem? It's not going to be any harder because it's a special case of the halting problem, so it's not going to be harder. But the question is it any easier? Because if I fix M to be a special program on the empty string, like begin, end, that's the whole program, obviously it's now very easy. But if I make this arbitrary programs, but make the input not arbitrary but fixed at empty, the question is that any easier than the halting problem? How many get that strategy or direction of where we're going? Okay, good. And this slide answers that question. And the answer, surprisingly, is it's just as hard as the arbitrary halting problem. How can that be? Well, here's the proof. Let's go through it again. So an arbitrary machine and an arbitrary string come in the door. That's an instance of the halting problem. It's an arbitrary instance. And I'm trying to solve that. I don't know how to solve that because, in fact, I know it's impossible to solve that. There's no algorithm for it. We already proved that. Turing proved that. We proved that. All right. So now we're going to show that if you can solve this apparently simpler version of the halting problem, namely the halting problem on the empty string, you can solve an arbitrary version of the halting problem from it. And here's how you do it, if that were possible, which it isn't, but if it were, this is how you were going to do it. I'll take this machine and that string that's arbitrary. I'm going to compile them into a program that internally runs that machine and that string if you ran this program, this purple program M prime. If you ran it, that's what it would do. Simulate that string on that machine. But it's not going to be run. It's going to be created as code. But let's say I have an oracle for the halting problem on the empty string. Let's say, this guy is the oracle. He always knows very wisely what the answer is for the halting problem on empty strings. Not the halting problem on arbitrary strings, the halting problem on the empty string only. Special case. But let's say he can do it. I'm not going to question how. He just does. But if he can solve the halting problem on the empty string, I'm going to use him to solve the halting problem on arbitrary strings. I'm going to, again, compile that arbitrary machine, arbitrary string into a new program that simulates that machine and that string. I'm not going to run this program. I'm going to give it to him. I'm going to ask him, what does this program do on the empty string? And I know that this program does on the empty string what it does on any string. It ignores it, and instead always does the same thing, simulates M and W, but that's the program I gave him. And according to the advertisement, he knows always what a program will do on the empty string. And so what do you say? Will it halt or not halt on the empty string, this program that I gave you? Won't halt. Okay. So I believe him because he's a wise oracle and he's always right. So he told me that this doesn't halt on the empty string, which means that M did not halt on W, because if you ran this program, it will take the empty string, ignore it, and run M on W and halt on the empty string if and only if M halted on W. That's what it's designed to do. It's easy to do. I'm doing this internally by compiling this little piece of code based on M and W. It's a simple simulator. M and W are hardwired into this piece of code. He tells me that this piece of code will run forever, which means M and W internally would run forever if you ran this, because he'd be right. He's an oracle. And so from that, I can infer that M and W must run forever, otherwise this will halt and he'd be wrong. But he's never wrong. He's an oracle. And there's a contradiction there. Right? Why is it a contradiction? Because if he's always right, I exploited him as a subroutine to solve an arbitrary instance of the halting problem. Arbitrary, not on the empty string, but arbitrary, even though all he can do is tell what programs do on the empty string, not arbitrary. Special case. So in using a special case subroutine, I've solved the general problem using this transformation. And it is a transformation. Again, I'm emphasizing for the 17th time, we're not running M prime. We're creating it and statically writing it on paper so that we can feed it to him and he can tell us what he does. He may run it, he may not run it. I don't care what he does. I just care that he's always right, always comes back with the correct answer. So basically, I showed you how if you can solve the halting problem on the empty string, you can solve the arbitrary halting problem, which means because the halting problem arbitrarily is undecidable, the halting problem on the empty string must be undecidable too. And that's the end of the proof. even though it's a special case. How many get this now? All right, it's a bunch of you. Good. Any questions? All right, it's a win. And this is a reduction. Okay. And let me ask you, see if you really understand it deeply. Let me just remind you, this is what we've just done. How many get that? We just mapped an A to a B. All right, then if you get it, what's the A, what's the B, and what's this function f in what we just did in the last 5 minutes? What's A and what's B? And what's f? Yeah. Yeah, so A is an arbitrary instance of the halting problem, right? And B is an instance of the halting problem on an empty string. And we transformed a member of A to a member of B. In other words, a member of the arbitrary halting problem to an M prime, a member of halting problem only on empty string. Okay, so that's the A and that's the B. They're both strings. A program is a string. A piece of code is a string. An algorithm is a string. A Turing machine is also a string, properly viewed. The description of the Turing machine is one big string between quotes. Right? Your favorite movie is a string. How's your favorite movie a string? Isn't this a video? Why is a movie a string? Yeah, it's a stream of bits. Take all the frames of the video, put them side by side. Each frame is a big JPEG or GIF or TIFF or whatever, image, and then, stretch them all out as bit strings and put demarcations between them so you know which frame is which. And it's one big string in a big file. It's 5 gigabytes long, and that's your movie. Right? Your entire genome is one big string. The entire description of you is a string, biologically speaking. So strings are pretty interesting things. They're not just A to the N, B to the N. Right? Shakespeare's Hamlet is a string too. Our textbook is a string. The entire biography of your life is a string. Okay, so strings map to strings. Programs map to programs. Turing machine descriptions map to Turing machine descriptions. And what is the F then? So we said A is the halting problem, B is the halting problem on the empty string. What is F? The reduction. It's the process of me taking this W that came in the door and taking this M along with the W and creating a program for it that does this and writing it all out. And that's the transformation. That's how I transform M and W into this M prime. F is the function that does that. You can write it as an algorithm. You can think about it as a little tiny compiler, however you want to think about it. I mean, it's not even worthy of the name compiler, because all it does is this obvious, simple task of taking these two strings and creating a simple piece of code that emulates that program represented by the first string on that input represented by the second string. Might as well call it a compiler. That's sort of what compilers do, is they take an input and produce a piece of code from it. That's what we did. Okay, so far so good, because we're about to generalize the heck out of this. It'll get a lot deeper in a minute. But before we do, let's go another example. Now you get the hang of this. See how it goes. So if I say, is the language of a Turing machine empty or not? It's a basic question, right? For finite automata, we answered that question. We gave an algorithm to how to figure out if the language of a finite automata is empty or not. Remember, we started the algorithm starting at the initial state, see if there's some path to a final state from an initial state. If there is, the language is not empty. How many get that? For finite automata, you can tell whether it'll accept something. Doesn't matter what. If there's a path from an initial to a final state, you're good. In a Turing machine, there's no way to do that. There are initial states, one initial state. There are final states, but it's no longer about paths, because the contents of the tape affect how you transition from state to state, and there's no way to keep of the infinitude of possible paths based on different states of the tape and so on. There's no algorithm for it. We're about to prove that. This is not a proof, what I just said. It's an intuition. It's a statement of the theorem, really. So if I want to know if the language of a Turing machine is empty or not, there's no way to do it, and we're about to prove that. How do we prove that? Well, so we're going to prove that the language of a Turing machine, whether it's empty or not, is not decidable. It will be a reduction from the halting problem. So here we go. An arbitrary instance of the halting problem comes to the door. And it walks in, and we're trying to figure out if this machine holds on this input. Right? Arbitrary instance of the halting problem. We don't know how to do that. In fact, we know it's not doable. It's impossible to do. There's no algorithm for it. Turing proved it. We proved it. Okay. But how do you use that to prove that whether the language of a machine is empty or not? That's undecidable too. So we're going to transform arbitrary instance of the halting problem as follows. We're going to construct this program here. We're not going to run this program. I'm saying it for the 23rd time. We're going to just construct it. The program will be constructed to do the following if it ran, but we're not running it. We're just constructing it to basically ignore its own input, right? Simulate M and W. This M and W that walked in the door, now they're constants hardwired into this program that we're constructing. This program is purple one, it's M prime. Right? So very similar to the last proof, almost identical to the last proof, in fact. If you remember what was on the previous slide, almost the same. In fact, so far it probably is the same. This new program that we're constructing has M and W hardwired into its code. There's two constants. It'll basically ignore its own input x, easy to do, and then simulate M and W internally, same as before. Okay. And so M holds on every input because it ignores it, if and only if so M prime holds on every input, if and only if M holds on W, because this M prime that I've constructed ignores its own input and internally simulates M on W. So if I had a oracle that could tell me whether the language of a machine is empty or not, I can exploit it in solving the halting problem from that, but with a single subroutine call. Okay. So again, we're not running this program. The oracle may do what they wish with this program, but we're not running it. We're just constructing it, and we give it to the oracle. So if he's an oracle that can determine whether the language of a machine is empty or not, I'm going to give him this program that we just constructed. There you go. And he will divine somehow the correct answer. And what do you say? But you're not supposed to tell me if it holds. You're supposed to tell me if the language of this is empty or not. Remember, empty, good. Okay. So the oracle tells me the language is empty. So what can you tell me about M and W if the language of this purple machine M prime is empty? What does that immediately imply about M and W? It doesn't hold. Because M and W holds for every single string if M holds on W, and it runs forever on every single string if M runs forever on W. Its behavior is pretty boring. Either it runs forever on every single thing you give it, or halts on every single thing you give it, based on what M and W does halt or doesn't halt. Right? So the language of M prime is either empty or what? What is the alternative? Or it's sigma star. Either it accepts nothing or it accepts everything based on what M does on W internally. Again, we're not running this program. We're giving it to the oracle. So if there's an oracle that can tell us whether the language of a machine is empty or not, we just exploited an oracle into solving the arbitrary halting problem for us in its full generality, which we know is an impossible task. Which means the problem that the oracle is supposedly solving is an impossible task too. Otherwise, both tasks would be possible. QED, end of proof. How many get this? This is almost the same proof as we had on the previous slide. If you don't believe me, can I get an eye full of this? And here's the previous slide. Whoop, the same thing, pretty much, except the result was different. Here we just talked about the empty string recognition. We saw that's undecidable. Here we're talking about the empty language recognition. And sure enough, the proof techniques was almost identical. Any questions on this? We're going to see a third example, and then we're going to dive into deep water. All right. Here's the third example. Again, very similar to this, with a slight twist, so you don't think they're all identical, but they're almost identical. I want to know if the language of a machine is regular or not. So I have a Turing machine, and the question is its language regular? And the answer is law of the excluded middle. It's either regular or not regular. There's no semi-regular or almost regular or regular a little bit. Language is either regular or not. Either there exists a finite automata for it or it doesn't. So it may seem maybe you should be able to answer that somehow. It's not exactly the halting problem. In fact, this doesn't look like the halting problem at all. We don't care what it does on any particular string. We just care if its language is regular. Now, for some Turing machines, its language will be regular. Others, it won't be regular. Give me 2 examples and go. Take only 5 seconds and go. When is it? Give me an example of a Turing machine whose language is regular, and also one that's not regular. At this point, a question like that shouldn't take more than 2.5 seconds. Yeah. Yeah, if it just accepts one string, it's a finite language and it's regular. And for the other example? Yeah. Anything that's not regular, like even 0 to the n, 1 to the n. You don't even have to be as esoteric as a halting problem, but you could say if a Turing machine accepts 0 to the n, 1 to the n, its language is not regular. It's 0 to the n, 1 to the n. It's not regular. It's context-free, but not regular. That's an example, too, and you can go many more examples. Okay. That question in general is undecidable. Why? So assume there's some oracle that decides whether the language of an arbitrary Turing machine is regular or not regular. Never mind how it does it. It just does. It's always correct. It has some magic, omniscient algorithm to do it. All right, here's what we do. An instance of the halting problem comes in. We take it. We hardwire it into this little program that we're writing. Now, it begins to sound familiar. And that program that we're now writing, we're not executing it, we're writing it. It's this purple program M prime. Is designed to look at its own input. And this time it does not oblivious to its input. It looks at its input. And if the input is something like 0 to the n, 1 to the n, it accepts it. If its input is not 0 to the n, 1 to the n, what it does next is it just ignores that input if it's not of the form 0 to the n, 1 to the n. Instead simulates the hardwired M on the hardwired W, the hardwired program, the hardwired input string from that instance of the halting problem that walked in the door. And we're not running it, we're just writing it. And so let's look at, before we even go to the oracle, let's look at what the behavior of this code would be if it ran, but we're not running it. But if we ran it, the language of this machine, M prime, this purple machine, will be what? If M halts on W, well, if M halts on W, what would be the language accepted by this machine? What will be the set of strings for this purple machine that we would halt on? Yeah. It'll be everything. Yeah. If M halts on W, it's either in this form, and if it's not of that, if the string is not of that form, it'll still simulate M on W halts, and if it halts, it will halt, it being the purple machine M prime. So either way, it will halt no matter what the input is, and therefore its language will be sigma star because it accepted everything that got through its door. How many get that? Okay, this is what it does. It's all it does. All right, on the other hand, if M doesn't halt on W, that's a little bit less obvious case. If M doesn't halt on W, and this will never be entered here, what will be the language of the machine, this purple machine M prime then? It wouldn't be sigma star. What would it be? Yep. It will be 0 to the n, 1 to the n. Because the first thing you do is look at the input. If it's in that form, you halt and accept. Doesn't matter what M does on W, because you never get the M and W. You just accept and bypass the rest of the code. So if the language of this machine is 0 to the n, 1 to the n, it must mean that M ran forever on W. If this language of this machine is sigma star, it means that this M halted on W. So all strings came through, the 0 to the n, 1 to the n, and everything else came through too, based on this second piece of code down here, steps 2 to 3 and 4. So either the language of this machine is sigma star, which is regular, which means M halts on W, or the language of this machine is 0 to the n, 1 to the n, which is not regular, which means M runs forever on W. And we don't know what M does on W, but there we have an oracle that can tell us whether the language of a machine is regular or not regular. And we don't care how it does it. But that's what an oracle is. It's a mysterious, omniscient entity that we always go to advice from. And all right, remember which oracle you are. You tell us whether the language of a machine is regular or not regular. What do you say? Regular. Okay, good. It's hard to go wrong. It's an oracle. Whatever the oracle says must be true. So there's no arguing with an oracle. Remember Matrix? Neo in the Matrix, there was this oracle there. Neo went for advice. And anybody know what I'm talking about? Yeah, good. Oracles appear in movies too. The Oracle of Delphi. The Greeks had oracles. I don't know how good the oracles were, but Greek kings used to base their states' decisions and futures on words of oracles. The financial world has an oracle. What am I talking about? Who's the oracle of stock investing? Warren Buffett, the oracle of Omaha. He's always right, apparently, about investing. There's an interesting little sideline about that. So many people trust what he says, and when he says a stock is good, everybody goes and buys that stock because they trust him, which means even if it was bad before he said it, once he said it, it's good because they're all buying it, drives the price up, and he's right yet again. So, there's self-fulfilling prophecy going on here. But never mind that. I digress, just so you know. All right. So an arbitrary instance of the halting problem came in the door. I don't know what it does, but I constructed this program whose language, this machine whose language is regular if and only if that machine halts on the input, and that oracle said the language is regular, so now I know the machine halts on this input. I don't have to do anything else. The oracle solved that problem for me, even though it was solving a different problem than my problem. I did a reduction. Right? Just like you're solving a different problem than trying to have a good income one day by being here, by solving the problem instead, it's a different problem, of getting a good education. It gives you skills that would get you good, well employed, and so on and so on. It's a reduction. How many get this? I think we lost some people from the last example. How many got the last example? There was more people. This is almost the same. The only twist here is that the program here that we're constructing, this purple M prime, doesn't always ignore its inputs. It does something with its input, not oblivious to its input all the time. And what it does to its input is it looks at it. We're not running M prime. It says so right here. I've said it many times. It's important to remember that we're not running M prime. We're constructing it that if somebody ran it, M prime would look at its input, see if it's equal to some form 0 to the n, 1 to the n. That's easy to do. Just check the number of zeros the same as the number of ones. If it is, accept and hold. End of story. If it's not, run internally M on W inside M prime, which is not being executed, but if it did, it would run M on W internally. And as a second step, do whatever M does on W to its input string. If M holds on W, it would accept the string. If M doesn't hold on W, it would run forever and thereby implicitly reject that string. So the language of M prime is either all strings or only these strings, 0 to the n, 1 to the n. In other words, either regular, sigma star, or context-free and not regular, 1 to the n, 0 to the n, 1 to the n. And this oracle will tell us which is which, and thereby solve the halting problem for us. Another reduction we just did. How many get it now? Well, if it's only going to be 10 of you, I'm reluctant to go into the next slide, which is Rice's theorem, which generalizes the heck out of this. So ask me some questions before we jump in there. Yeah. It's never a run. Remember, I said it many times. And the reason I said it many times, because I knew there'll be this confusion that you're just confirming now. So thank you for doing that. Vindicates me. How did I know there'd be so much confusion about whether we're running M prime or not M prime? Because I've been having this conversation for almost 30 years with people. That's how. Question? Well, because for the same reason it's important that you don't take M prime and plug it into your iPhone and try to tweet using it. I mean, you could try, but that wouldn't accomplish anything. You see? So we're not running it for a number of good reasons. Is because doing other things with, like running it and trying to make it into a Twitter bot or whatever, will be an exercise in futility. it's not necessarily impossible, but it's not going to prove the proof. Secondly, another reason we're not running it is if you did try to run it and M ran forever, you would run forever from it, and you wouldn't know the exact answer, yes or no, to the question we're trying to ascertain. You see? So if you want to know yes or no for sure, and in the process of trying to figure out the answer, you inadvertently attempt to run something that may run forever, and you blindly run it without any recourse to anything else, you're risking yourself running forever with it, and you'll never know the answer, because there's no end of forever. There's no time after forever. Forever is a long time. There's no room after the last room of an infinite hotel, not because you can't find the room after the last room. It's because there is no last room to look after it. So it's another reason why we're not running these things. One, it won't accomplish the job. It won't prove the theorem. Two, you're risking running forever along with it if you run it. But if you go to the oracle always knows the answer, and he may or may not run it. It's up to the oracle. If he wants to run it, that's okay. But maybe he has some clever way to run it while observing its behavior, while trying to figure out that it's an infinite loop, and then abort it, and then avoid thereby running forever. I don't know what the oracle does. It's a black box. But I'm showing you through this proof that no matter what it does, it can't be an algorithm, because I can take his algorithm over here, no longer a black box, but if he had an algorithm, I can take that algorithm over here, incorporate it into here, run his algorithm on this piece of code, the super duper compiler of his, whatever that algorithm is, on this piece of code, and thereby tell whether the language is regular or not, and thereby tell whether M holds on W or not, and I'll be solving the halting problem with code, with an algorithm, which we know is impossible. So the conclusion is, however he does his job as an oracle, can't be an algorithm. Because if he was, we would take that algorithm, wrap it around into here, fold it into here, and we'll have in a slide a whole algorithm for the halting problem, which we know can't happen because such an algorithm doesn't exist. It's a very dramatic, audacious statement to say an algorithm doesn't exist. It's not so dramatic to say, well, I couldn't find one. Oh, fine. Maybe you didn't think hard enough. Maybe you only put 10 years of work into it and not 1,000 years of work. Maybe that's why you couldn't find one. But if you say I couldn't find one, because nobody can find one, however omniscient, infinite intelligence, however omnipotent, all-powerful, can't find one either, because it doesn't exist. That's a much stronger, more audacious, more unbelievable statement to be able to make. And when Hilbert gave his list of 23 problems back in the year 1900, remember, one of them was find an algorithm to determine whether arbitrary polynomial equations have solutions and blah, blah, blah. It didn't even occur to him that such a scenario is possible. People said, if you can define a problem well enough, precisely enough, unambiguously enough, there's got to be a way to solve it. If you can show that answers always exist, there's got to be a way to find those answers. The answer especially is either yes or no, like the halting problem. So the answer always exists. For every piece of code, the answer is either yes or no. There's no ambiguity about that. But the algorithm, supposedly, that would find out this answer, that's what doesn't exist. And to be able to prove that, you got to prove you're not a millionaire. You got to cover a lot of ground. You can't just show people your checking account and say there's $7 in there, QED. I'm not a millionaire. You got to do a lot more than that. In fact, it's impossible to show that you're not a millionaire. Very, very difficult. To show that you're a millionaire, that's easy. Right? So it's a proof by contradiction. It's a non-existence proof. And Hilbert was the smartest mathematician on the planet in the year 1900, maybe even by today's standards. And he asked a question, and by asking it, he made a type error. The question was valid. How do we figure out whether polynomial equations have solutions? It's a valid question. It's a very precise question. There's either solution or no solution, right? I mean, a squared plus b squared is c squared. It's a Pythagorean theorem. It either has solutions and it doesn't, and it happened to have solutions. Right? 3, 4, and 5 is a solution to that equation, Pythagorean theorem. And there's many other solutions. But a cubed plus b cubed c cubed, there's no solution to that. It's corollary for Fermat's last theorem. So either an equation has a solution or it doesn't have a solution. And he said, good, then somebody should find an algorithm for it. He didn't say, does there exist an algorithm for it? He said, somebody find one, assuming it must exist. He was wrong on that. In a very subtle way. It didn't occur to anybody on the planet that there's some problems which are so well defined for which an algorithm can't possibly exist. That was inconceivable. Right? Didn't occur to anybody that could be the case. Not even to Hilbert, not even to Einstein, until Turing came along in 1936. He said, wait guys, not everything that can be easily stated, unambiguously formulated, even with a yes-no question, has an algorithm. And here's an example, the halting problem, and there's an infinity of other examples, and we just showed you several more. And I'm about to show an infinity of examples. In fact, an uncountable infinity, and that's Rice's theorem. And we're on the edge of the cliff here. I want to make sure we're all good before we take the plunge. Does that make sense, everything I just said? Not just why it's true, but also why it's unbelievable almost that it is true. Why it was so hard for humanity to come to this conclusion less than a century ago. For thousands of years we thought about algorithms, right? People were adding, subtracting, taking square roots, and doing Pythagorean theorem calculations back in ancient Greek times. But even recently, they thought that every Boolean formula must have an algorithm to compute it. That's what we all thought as a species. We were wrong about that. The halting problem is one such counterexample. And I just showed you three more. And Rice's theorem will show an infinity of more, and not just a countable infinity, but an uncountable infinity, which means most problems have this property. That's the big shocker that's coming next. It's not just the halting problem that has this issue. There's no algorithm for it. It's not just these three examples I just showed you, whether the language of a machine is empty or not, whether it's regular or not, whether the machine halts on the empty string or not. Not just those three are undecidable. There's no algorithms for them. There's an infinity of other problems. And in fact, an infinity is uncountable. And the infinity of the problems for which there is an algorithm, that's countable. The set of all algorithms, set of all Turing machines. You can enumerate them, count them. 1, 2, 3, 4, range them in lexicographic order, dovetail, lexicographic order. So there's only a countable number of problems that we can solve, and an uncountable problems that we can't solve. They far outnumber the ones that we can do. It's amazing we can add two numbers together. That's what the bottom line is here. It's probably the most negative result I can think of, the most depressing result I can think of in theory and in computer science and in mathematics, is that almost any problem that you can name, almost any function that you can write down, even well-defined ones that are everywhere defined and they're binary, they're Boolean, they're undecidable, they're uncomputable, there's no algorithms for them. So the things that we can't do, even in theory, far outnumber the things we can do. It's not just a fluke called the halting problem, some esoteric, strange case. It's almost everything. That's how ubiquitous undecidability is. Okay? It's hard to over-dramatize it. It's pretty darn dramatic. All right, any more questions? Yeah. It doesn't. X is just a string coming into this box. It could be any string in sigma star. Why is it useful for it to accept these? Because if it does accept these, the language of this machine in purple will be 0 to the n, 1 to the n, which we know is context-free but not regular. As distinguished from if this m halts on w, the language will become sigma star. It'll be 0 to the n, 1 to the n, and everything else too, which makes it sigma star, which makes it regular. So in one case, the language will be 0 to the n, 1 to the n, not regular. On the other case, it'll be sigma star, regular. And then the oracle will tell us which is which. Unambiguously, we'll be able to tell from his answer whether m halts on w or not. It's an if and only if. That's why 0 to the n, 1. You could have made it some other language like palindromes, or 0 to the n, 1 to the n, 2 to the n, or any other non-regular language here. It doesn't have to be 0 to the n, 1 to the n. It has to be some non-regular language that's still decidable. Does that make sense? Good question. Good question. Okay, what else? Ask me more stuff. No questions? All right, Rice's theorem. With all that we build up, this really better be good, right? Okay, so we're about to prove that not only these three examples are undecidable, almost anything you can imagine is undecidable too, which is a pretty pessimistic situation. All right, so define a property of languages, of recognizable languages, simply to be the set of those languages. So a set P1 is the set here in this example of all decidable languages. That's a subset of all the recognizable languages, but a property is just a set of languages. I'm not attributing any kind of meaning to that other than it's just a set of languages that has this property. Right? So if property says the set, for example, of all context-free languages, the property is just the property of a particular language is whether it's context-free or not, whether it's an element of this set or not, of languages. It's not a set of strings, it's a set of languages. It's a set of sets of strings. The braces are nested too deep here. Make sure you understand the type. Okay, so these properties are not languages, they're sets of languages. How many get that? Okay, cool. So here's the set of languages as a property of all languages are equal to their own clean closure. You know, some are, some aren't. Sigma star is, 0 to the n, 1 to the n is not. Okay, so some languages are an element of this property, others are not an element of this property. Here's a property that only has one language, the empty string language, not the empty language, the empty string language. This property is empty. This property has no languages. P5 has no languages in it at all. That's okay. P6 is all recognizable languages, so that's all of them. Right? So that's the complete set of languages in there in P6, which means every recognizable language has this property. It's an element of P6. Okay. So L is said to have a property if simply it's a member of that set. Okay. So it's just so far just a definition and a few examples. So for example, A plus B star, sigma star, has property 1, 2, 3, and 6, but not 4 and 5. Why? Because it's a decidable language, sigma star, sure. It's a context-free language, yeah. Okay. It's equal to its own clean closure, sure. It's sigma star already. The clean closure of sigma star is still sigma star. You're not going to get any more strings than sigma star. So it has property P3, but it doesn't have property P4 because sigma star is not an element of this set P4, and it's certainly not an element of this set P5 because P5 is the empty set. Nothing is an element of it. In particular, sigma star is not. But it is a recognizable language because we can recognize it with a simple finite automata, and certainly with a Turing machine, certainly with an algorithm, but even a finite automata can do it. So certainly recognizable. It's even decidable. In fact, it's even regular. So how many get that so far? Just a couple of definitions, a couple of examples. So for example, all palindromes, the set of all palindromes has properties 1, 2, and 6, but not 3, 4, and 5. You can check that. So a property is trivial, quote unquote, that's a definition, if it's equal to the empty property, i.e. P5, or all languages, that is P6. So these two properties are trivial because there's a very simple algorithm to determine whether a recognizable language has this property P5. What's the algorithm? And by the way, before you even answer that, how do I present to you a language? I can write down all the strings if it's finite, or I can write down a regular expression for it if it's infinite but regular. But in general, how do I hand to you a language so that you may know what language I'm talking about? Write a grammar for it? What else? There's many ways to do it. It's a good way. What else? It's not a hard question. It's not a trick question. In fact, none of these questions are trick questions. Yeah. You could, but in general. So if you're talking about a set of prime numbers, talking about a set of perfect numbers, a set of perfect squares, a set of numbers that satisfy a certain equation, the set of all movies that were produced as strings, that's a language. You know, how do you hand over a language? The set of all valid C programs or all valid Java programs. How do I give you that language so that I convince you of what it is and that we know what we're talking about? Yeah. Yeah, give them a machine that accepts that language, and they now know unambiguously what that language is. It's the language of that machine. There's no ambiguity about it. Whether a string is actually a member or not a member, that's a different story. And that, whether it's an algorithm or no algorithm for it, that's a different story. But they at least know what the language is. It's a language accepted by that machine or that program or that piece of code or however you want to think about it. How many get that? And these machines, these grammars even, can be represented as a string. So I can give you a string, and with that string, I can completely and unambiguously, uniquely define a language for you. Whether that machine lists all the elements if it's a finite language, or gives me some general rule, or a regular expression, or a machine, or a piece of code, or a grammar, however you want, or an English description. I can say the string is a piece of code that accepts all prime numbers and rejects all non-prime numbers. Now you know exactly what infinite language I'm talking about, this set of primes. And that's a finite string. That English description was enough even. I don't even need to give you the code. I can just give you that sentence. The set of all integers who each have only at most two divisors themselves and one. End of story. So that's a set of primers. So, okay, now you know how to specify a language. Of course, you knew this all along. I just want to make sure you remember that. Right. So back to this question. If I say, I give you a language, now you know what it means to give a language. I give you the grammar, I give you the algorithm, give you the Turing machine, give you the English description. I give you a language. What's your algorithm to tell me whether it has property P5? And let me give you a hint. That algorithm has one line of code in it. So it's not hard. I see a hand went up and then went down. What do you say? Yeah. So the algorithm simply print out, quote unquote, no. And you'd be right. That would be the algorithm. No language has that property, so a print statement just blurting out no would always be correct. How many get that? No. Not hard to do. So P5 has a very simple algorithm, one-liner. Can't be any simpler than that because no algorithm has 0 lines. It's got to have something in it. Right? All right. Which algorithm solves P6? If I give you a language as a Turing machine, by definition, Turing machines' languages are recognizable. Right? A set of recognizable languages is exactly a set of languages of all Turing machines. Always say yes, and you'd be right. So these two have very simple, trivial algorithms, just yes or just no, and one of these two will be the right algorithm. And here's the kicker. Any other property, not just these ones up here, but any other property besides these two trivial ones that have a one-line algorithm, have no algorithm whatsoever. It's an extreme situation as you can imagine. It's hard to get more extreme than that. And we're about to prove this. Okay? So these are the two trivial properties. The algorithms are obvious. And those are decidable. We just gave the algorithm. So for this property, the algorithm would just say no. Right? Just like the Nike commercial, just say yes or just say no, whether it's Nike, whether it's drugs, I don't know. One or the other. And for the other one, you just say yes. And those are the algorithms we just mentioned. So I'm just nailing down the notion that these two trivial properties have algorithms. One is just yes, one is just no. And then what other properties have algorithms? None. No other property besides these two have algorithms, and there's an infinite number of properties. In fact, an uncountable infinite number of properties. Why? Because there's a countable number of recognizable languages. You can enumerate the Turing machines, count them, 1, 2, 3, 4, by lexicographic order, length of description, whatever. And then a property is just a subset of those. How many subsets are there of a countable set? An uncountable set of subsets. Right? It's the power set. Okay, here it is in its full glory. Very short theorem. All non-trivial properties of Turing recognizable language are not decidable. That's what we just said. All right, and what we're about to do in the next 10 minutes is generalize the last 3 examples. So let P be some non-trivial property. Not those two that are easy, but some other one that's not one of those two. And we'll see how hard it is to compute them, and the answer will be undecidable. All right, so without also generality, if the empty language is an element of the property that you've chosen arbitrarily, except those two trivial properties, if the empty language is one of those languages in your property, then prove what we're about to prove for the complement. I want the empty language not to be there. You'll see in a minute why I want it not to be there, because it'll make the proof work, basically. But if it is there, all you got to do is negate that property and prove it about the complement of that property, because a property is decidable if and only if its complement is decidable, because you can invert yeses and nos. So you can't have that something is decidable and its complement language is not decidable, because if the complement is not decidable, the complement of the complement is the language itself. Right? So together they stand, together they fall, a language and its complement with respect to decidability. Because if a language is decidable, so is its complement. And if the complement is not decidable, the original language can't be decidable either. Otherwise, the complement would be decidable again. Because you can just take the algorithm for the decidable one of the pair, negate it, and it'll be an algorithm for the other one. How many get that? So we're going to prove it either for P or the complement of P, depending on whether the empty language is an element, not a subset, an element. Because P, remember, is not a set of strings, it's a set of languages. The braces are nested too deep. Okay. So select some language in this property, because it's not a trivial property, so there is some language in there, and that language can be not the empty language, because we made sure that the empty language isn't in that property. So whatever language, arbitrary language L, we take out of this property, select arbitrarily, we know for sure it's not the empty language, and we know for sure it's not, and we know for sure it exists, because the property is not trivial, so there's something in there, and that something isn't the empty language. All right, so let the machine M sub L, I'm just calling it something arbitrarily, recognize that language that we picked out of the blue, out of this property. So a property comes in the door, we're trying to find out how to decide it. We'll see that we can't, and towards that, we'll pick some language out of that property, because it's just a set of languages. That's all a property is. And let the machine that recognizes that language be called M sub L. I'm just giving it a name. Right? Because remember, those languages are all recognizable. There's a Turing machine for each, and the Turing machine that recognizes L is just M sub L. I'm just naming it so we know what we're referring to when we talk about it. Okay. So assume towards contradiction that there is some algorithm, some piece of code, some oracle, that decides whether a language has this property P. And P is a non-trivial property. So that oracle exists, it's doing something. Okay. It's deciding the property P. It always says yes or no. Right? Towards contradiction, we'll see that can't happen. And we already mentioned, what does it mean to specify a language? How do we give this oracle, this black box subroutine, this piece of code, a language on a silver platter? Well, either give it the grammar, either give it the Turing machine, either give it the English description. There's lots of ways to do it. All right, here's the reduction. So we're going to use the machine of that property to solve the halting problem for us. Right? So an arbitrary instance of the halting problem comes in the door. And you're beginning to see how it's going to generalize the last three examples. So into the door comes in a machine and a string. It's an instance of the halting problem. We don't know how to solve it, but we assume the oracle can solve the property P. Okay, and using that oracle, we'll solve the halting problem by exploiting it as a subroutine. All right, so we're going to construct a Turing machine or an algorithm. We'll call it M prime. It's that purple M prime. Now it's red, I guess. But for this arbitrary machine and string that's coming to the door, instance of the halting problem, arbitrary instance, we're going to construct this new machine. We're not going to run it. We're going to construct it. This M prime that takes its input, whatever it is, but before it even does anything with its input, M prime is not being executed, it's not being run, but if it did, this is what it would do. Internally, there'll be hard-coded M and W into its code as constants. So M is a constant, W is a constant. Once they came in the door, we're constructing M prime as a function of these two. Same as before. It'll run internally M and W, simulated, and if it halts, it will then run the decider that supposedly solves, that accepts the language L out of this property P. Remember, we picked L over here, right, out of this property such that it's not an empty language, and it's got to be there because the property is not trivial. So the machine for L is right here. So if M holds on W, it'll fire up this machine M sub L. And M sub L will be run on the input to M prime. And if the answer is yes, we'll say yes. Otherwise, we'll just keep simulating M sub L. And by yes, we mean hold and accept. So if M sub L accepts, we will accept. The red M prime will accept too. So that's how M prime is constructed. The question is, what is its language? So its language is either one of two things. The language is either the empty language. If M on W never halts, this part of the simulation will never start. That start button will never be fired, and this will never execute, because this will run forever. And so the string will not be accepted. And if this runs forever, M and W are the same for every string X. And if this runs forever, the blue M and the blue W is this pair here. If this runs forever, this start button will never be pushed, and M prime will not accept any of its strings, which means the language of M prime will be the empty language. On the other hand, if M holds on W, this will be fine. It will say halt eventually. The start button will be pushed. This simulation will start, simulating M sub L on X. And then whatever M sub L accepts, the red machine M prime will accept, but the language of M sub L is simply L. That's how we picked M sub. That's what M sub L does. It's the language, it's a Turing machine that accepts the language L. And so the language of M prime will become the same as the language of L, because that's what M prime is doing at that point, is simulating M sub L, resulting in its language. So the language of this M prime, this red machine, it will be either the empty language or whatever the language of M sub L is, which is just L, that language we picked out of the property. All right, but remember, the empty language is not part of our property. L is. That's how we picked L. That's why we made the property not have the empty language in it. So if there's some oracle that tell us where the language of this machine M prime has this property, we know that M would halt on W. If it doesn't have this property, M will not halt on W. And if you have some oracle now that will tell you if the language of that machine M prime, the red machine, will have this property or not, that tells us whether M halts on W or not, which means that property is undecidable because the halting problem is undecidable, and we use that property decider to solve the halting problem for us. And this generalizes the last three examples. Okay, so there's no way to decide a non-trivial property, because if there was, you'd use this reduction to decide the halting problem, which we know you can't do. How many get this? At least in principle, not necessarily. Good. That's a lot of people. It's about a third of the class. That's more than I expected. This is pretty abstract. It's certainly more abstract than the last three examples, which were not easy to begin with, because this subsumes all of them. So what does that mean? That any non-trivial property cannot be decided. There's no algorithm for any of them. Okay. Which is pretty pessimistic, because there's only two properties that are decidable. The easy ones, the ones that's always yes, always no. There's only two of them, no more. And there are algorithms for deciding them, one line of code. The algorithm for deciding all the other properties, of which is an uncountable infinity of, not one line of code, not a billion lines of code, not a trillion lines of code. No lines of code will ever accomplish any of them. That's amazing. It means almost anything you can think of is undecidable in terms of properties of languages. I should make sure that you understand. It's not just anything at all, like addition or multiplication. Those are perfectly fine, luckily for us. But properties of languages, not decidable unless they're trivial. Again, I'm noting that we're not running this machine M prime. Okay. Immediate corollaries, make up any properties that you want that are not trivial, become undecidable. So for example, if the language of a machine is empty, it's undecidable. The language of a machine is finite, undecidable. If it's infinite, cofinite means the complement is finite. Is it regular? Is it context-free? Undecidable. You can't tell anything about machines hardly, about the languages of machines, not the machines themselves. If the language is a sigma star, if it contains an odd string, odd length string, if it contains any palindromes, if it's a language that's exactly the two words hello and world, undecidable. If the language is anything more complicated than the trivial two properties, that every language has that property or no language has that property, in which case the algorithm is either yes or no very easily. Any other properties, undecidable. Now, here's the, again, warning. I already said this, but I'll say it again. I'll write it down for you. I'll put it in red. Rice's theorem, this thing applies to properties of languages, not to arbitrary things. So if I say, does this Turing machine has 7 states? Yeah, it's very easy to tell if it has 7 states or not. Count them. See if they add up to 7. But that's not a trivial property. So what went wrong? What went wrong is you applied Rice's theorem to something other than the type of objects to which it's intended to apply. You applied it to a machine, not to languages, not to a set of languages. So you applied it not to a property, you applied it to something else. It's like saying, is my right shoe regular? Well, you can scratch your head and wonder about that, but you know, regularity is not a property of shoes. It's a property of sets of strings. It's like saying, is the integer 3 purple? Well, you can argue about it as much as you want, but the question doesn't make sense. Colors don't apply to numbers, right? So be careful what objects you apply this theorem to. Some of you will do it wrongly. I can tell you that right now, because it happens every single semester. On an exam or in your thinking or in your solutions. Remember what the types of objects that you're dealing with are. If you don't know the type of an object, you don't know the object, for sure. Right? If you don't know it's a mammal, you don't know that it's a horse. Think about it. Because if you knew it's a horse, you'd know it's a mammal. Goes without saying. But if you don't know whether it's a mammal or not, and you say it's definitely a horse, well, how do you know if it's a horse if you don't even know it's a mammal? Because a horse is a mammal, so you should know for sure. So, you know, how many get this subtle point? It's important. Keep that in mind. Apply things to the correct types of object to which it's permissible to apply these things. Right? You cannot feed an apple to a Turing machine. I know it sounds facetious, but that's exactly the kind of error a lot of you have made already and will be making some more of. So be very cognizant of that. All right. Any questions about any of this? It's a very dramatic result. Yeah. Black box, yeah. Yeah. And it's a very good point. So she's saying, you know, is an oracle a black box? Yeah, it's a black box. Why is it a black box? Why aren't we allowed to peek inside? Why aren't we saying inside is Java code? Because all we'll be proving if we say inside is Java code is that there's no Java code that can do the job. But that doesn't mean there's no C code that can do the job, or assembly code, or machine language, or some other clever computation device. Some sort of a DNA computer like ourselves. We are a DNA computer. We work on goo, on proteins. Right? We don't work on silicon and electricity. Actually, we work a little bit on electricity too. Our nervous system is electrically operated in principle through neuron firings. There's electrical potentials in our body. So we too work on electricity, actually, but not on silicon and not on transistors per se. So if we say an oracle has a particular kind of machine or algorithm, then the result only applies to that. So we want to make sure we don't look inside on purpose. So whatever it is we prove is true to whatever kind of code or program or machine that's inside. How many get that? That's important. What it doesn't say that if there's some magical creature inside, that the theorem will still hold. There could be a gnome or an elf or some magical kind of omniscient creature inside that always knows the answer. That's okay. The theorem doesn't preclude that. The theorem doesn't preclude magic. Maybe there's some Harry Potter kind of character with a magic wand that, puts a spell on the problem and always comes back with the right answer. We're not disproving that. That may very well happen. But what we're proving is that that magic spell inside the box cannot be simulated with an algorithm. It cannot be C code or Java code. It's something else other than code or algorithms. Any conceivable code or any conceivable algorithm. That's what we're proving. How many understand that? That's an important point. It's a subtle, almost philosophical point, but that's what the situation is. Right? We're saying no piece of code can do that. We're not saying no magic wand can do it. Okay? What else? Other questions? Yeah. Yeah. So what is M sub L? So what is L to begin with? So L is this language we pulled out of the property arbitrarily. It's an arbitrary member of this property. But it's not the empty language. This property is a set of languages, and L is one of those languages in the property. M sub L is simply the machine that accepts L. It's the machine that goes along with L. L is a language. It has some Turing machine that goes along with it. Because it's a recognizable language. Remember, the theorem applies to recognizable languages. I'm not talking about other non-recognizable or arbitrary languages. Recognizable language. So every language in the property has a Turing machine that goes with it. Because language is recognizable if and only if there's a Turing machine that accepts it. So what is L? L is a language we pulled out of this property arbitrarily. M sub L is its machine. The machine that accepts it. The machine that recognizes. Does that make sense? Okay. Good question. Any other questions? So that's a lot. Basically, it says almost any property you can name of other than the two trivial ones are undecidable. It's properties of languages, not properties of other objects. It's not properties of machines, not properties of apples or giraffes. It's properties of languages we're talking about. That's important. You know, be careful what a theorem, not just what it says, but what it doesn't say. Don't just throw it around wildly, aimlessly at things. Okay. And it's mentioned in the book on page 213 right there. Notice it's given as an exercise. Admittedly, it has a star by it, and it also has the answer by it somewhere else. But and then, of course, the book also proves the halting problem. You know, we did that really early on because the book is not necessarily a sequential set of prerequisites, right? The halting problem we proved pretty easily when we talked about Turing a couple of months ago, and that was fine. We didn't have to wait until we get to page 173 in the book. But here's that diagram that shows you the regular languages are a subset of the context field languages, which are a subset of the decidable. I'll give you a much bigger diagram with colors and showing you, a lot more than these four categories. That's okay. There's my diagram. And sure enough, there's the regular languages, and there's the context field languages, and there's the decidable languages up here, and finally the recognizable languages outside those. And the halting problem is one example. And by the way, all these green ones are examples of a language that's one of those, but not one of the type of the lower subsets that are properly contained in those, right? So for example, A star is regular, and A to the n is B to the n is context-free, but not regular. And A to the n and B to the n, C to the n is decidable, but not context-free, and so on and so on. The halting problem is recognizable, but not decidable, so it's out here, but not inside there, and so on. It's a Venn diagram, set containment, and most of these containments are proper. And of course, the complement of the halting problem is not even recognizable. The complement of the halting problem is all machines that don't halt. That's out here. It's not even recognizable. And then, of course, there are things that are not even finitely describable because there's an uncountable number of languages, but only a countable number of descriptions. You can sort them by size and within size like graphic order, dovetail through all the descriptions, countable number of descriptions, even in English, never mind Turing machines or programs, all countable. Number of programs, number of languages out here, 2 to the sigma star, the power set of sigma star, not countable. So most languages are not decidable, and most languages are not even finitely describable. We can't even talk about them because we wouldn't know what we're talking about because their shortest description is infinite. And here we are only talking finite to each other. Any questions about any of this? So now you know more of this landscape. And as we go forward, we'll start exploring sort of the middle ground between context-free and decidable, polynomial time and non-deterministic polynomial time, p is equal to np, intractability. This is even more subtle because now we're having a stopwatch in our hand watching our time and space consumption, not just what we can or cannot do. Yep. Deterministic context-free, this is deterministic. Deterministic context-free is context-free without the use of non-determinism. So 0 to a to the n, b to the n, we can recognize without non-determinism, using a push-down automata that doesn't need to do anything non-deterministic. But palindromes, WWR, we need non-determinism for, because we have to guess where the middle is and start popping against pushing. And okay, so good question. Question? To which? I didn't get that word. Super tasks. Oh, super tasks. Yes, it is actually. They're related. Let's put it that way. There's a paper on the class website talking about Turing and hypercomputations and super tasks. Read that paper. It's just a few pages, Scientific American paper, and then you'll know a lot more about that. But the two are related. You're right.